So, welcome to our discussion of heteroskedasticity once again. And if you recall, yesterday in our last class, we were discussing about Goldfeld-Quandt test for detecting heteroskedasticity, right? And then we also discussed about some of the major limitations of this heteroskedasticity detection by Goldfeld-Quandt test, and the major limitation was that in Goldfeld-Quandt test you need to arrange your explanatory variable from smaller to the bigger ones. That means if you have only one explanatory variable, while it is quite easier to arrange your explanatory variable from small to big, but when you have a large number of explanatory variables and you are not sure about which particular explanatory variable is creating heteroskedasticity problem, then basically you need to repeat the same procedure of Goldfeld-Quandt test for all the explanatory variables, which is quite time consuming process, right. Based on that difficulty, econometrician they have developed another test which is called Breusch-Pagan-Godfrey test, or in short Bpg test, right, Bpg test. Before we go ahead with the Bpg test, if you recall yesterday I said that all these tests based on which particular assumption you are making about your sigma square, that means error variance. In all these models, what we assume that sigma square is basically, so once again we are discussing heteroskedasticity. So, what we assume that sigma square I is actually a function of your explanatory variable, where x is basically explanatory variable. This is a function of x, and these different tests are developed based on which specific functional form you are assuming for fx, right. So, in Goldfeld-Quandt test, GQ test, Goldfeld-Quandt test, what you assume that sigma square I equals to some sigma square into xi square. So, that means sigma square I is basically an increasing function of x, it is xi square. So, that means as x increases, sigma square I increases at an increasing rate. Because of this particular assumption, the way we constructed the test statistic, how we have constructed the test statistic in Goldfeld-Quandt test, if you recall, that was RSS 2 by its corresponding degrees of freedom and divided by RSS 1 by its corresponding degrees of freedom, right. What is RSS 2? RSS 2 is basically the RSS from the model wherein you are running a regression of y on x, and x is from the second sample. You have arranged the data, you have arranged the x variables according to their magnitude. So, second sample consists of the larger values of x, larger, and the first sample consists of the smaller values of x. So, obviously, because of this particular assumption, that sigma square I equals to sigma square into xi square, RSS 2 should be quite higher than RSS 1, okay, RSS 1. Now, this particular test will follow the F statistic. Now, larger the difference between RSS 2 and RSS 1, greater would be the value of F and greater would be the probability of rejecting your null hypothesis, where null is basically homoskedasticity. Sorry, this is homoskedasticity. So, you can reject the homoskedasticity assumption. That was the procedure we discussed about in Goldfeld-Quandt test, right. Now, today what we will do, we will discuss about Breusch-Pagan-Godfrey test. Breusch-Pagan-Godfrey. In short, this is called Bpg test. So, here also what we assume, sigma square I is a function of f(x), and what is the specific functional form they have assumed? They have assumed sigma square I equals to some alpha 1 plus alpha 2, let us say z1I plus z2I, sorry, alpha 2 or alpha 3 z2I plus alpha 4 z3I plus alpha m zmi plus ui. That is the specific functional form they have assumed, okay, in Breusch-Pagan-Godfrey test. All right. And what is this z actually? If your original model is this, let us say that your original model is yi equals to beta 0 plus beta 1 x1I plus beta 2 x2I plus beta k xki plus ui. This is your original model of interest. So, that means we are interested to see whether heteroskedasticity exists in this original model, in this data set, right. Now, this z basically, this z, the set of variable that consists z coming from all or some of your x variables, right. That is the assumption that we make. So, we assume that all or some of your x actually consists this z. Z1 might be x1, Z2 might be x2, like that, right. So, all or some of your x is actually z. So, you can write this equation as in terms of x also. So, what you need to observe here, look at the way I have specifically mentioned the nature of fx here vis-a-vis in the context of Goldfeld-Quandt test, right. This is the procedure. Now, in Breusch-Pagan-Godfrey test, they have also given certain steps, and I will now discuss about the tests. So, this is Bpg test, So, step 1, and your model is yi equals to beta 0 plus beta 1 x1I plus beta 2 x2I plus beta 3 x3I plus beta k xki plus ui. This is your model, and what is your step 1? So, in step 1 they say that you estimate this model, this is, let us say, from this is model 1, you estimate your model, and then from this model estimate model 1 and get the RSS. And from RSS, what they are asking you to calculate some kind of, let us say, sigma tilde square, which is basically nothing but RSS divided by n, RSS by n, okay, RSS by n. Now, what is RSS by n? RSS by n is actually, if you recall, that RSS RSS by n minus k equals to, we said that this is basically sigma hat square from that OLS model. That means, if you divide the RSS by n minus k, what you will get? You will get the sample statistic of the sigma square. Sigma square is the error variance, which is unknown population parameter, and the sample counterpart of sigma square I is basically sigma hat square, which is coming from your OLS model, that is RSS by n minus k. Here, when I am doing RSS by n, that is basically the estimate of sigma square coming from the ML method or maximum likelihood method. That is the difference. So, both sigma tilde square and sigma hat square, they are actually the sample statistic or sample counterpart of the true population parameter sigma square, which is unknown. So, we are, since in presence of heteroskedasticity, sigma square I is actually biased. Sigma square I does not reflect the true sigma square. We are trying to get sigma tilde square from the maximum likelihood method. And how we are defining? This is basically RSS by n. Okay, this is basically RSS by n. Then in step 2, what they say that once you rectify your sigma square by sigma tilde square, then what you generally need to do, you just divide your ui hat square by sigma tilde square and define that as p. Okay. So, what I am doing, since your error variance is disturbed in presence of heteroskedasticity, look what I am doing. I am just correcting, I am just adjusting the ui hat square by this new estimate of sigma square, which is sigma tilde square, and I am defining that as p. That is your step 2. Then in step 3, or they say that you regress this p, equals to your all your explanatory variable. That means, you regress p equals to some lambda 0 plus lambda 1 x1 I plus lambda 2 x2 I plus lambda k x k I plus epsilon I. So, you have to run a regression of p on this, and what you have to do, you have to and collect the ESS from, let us say this is model 2 from 2. Okay. Then in step 4, what they say, in step 4 basically they say that half of ESS follows a chi-square distribution where degrees of freedom equals to m minus 1, where m is the total number of parameters in the look at what we are saying, m is this. So, total number of parameters in this model, total number of parameters here, okay, total number of parameters. Where m is the total number of parameters in the original model. So, if this calculated f, then the decision is that if the calculated f is greater than chi-square tabulated, okay, then you reject your H naught. And what is our H naught? That there is no heteroskedasticity. Okay. So, that means if you think about the logic or philosophy of all these tests, then things become very clear to you. In Goldfeld-Quandt test was also based on two RSS, RSS2 by RSS1. Why? Because we assumed that sigma square I equals to some sigma square multiplied by xi square. So, sigma square I is basically a increasing function of x. So, that is why we divided the entire sample into two, one consists of smaller value, another consists of higher value, and then we are taking RSS2 divided by degrees of freedom divided by RSS1 by its degrees of freedom. So, that means this RSS2 by degrees of freedom is what? That is nothing but sigma hat square, sigma 2 hat square. And what is RSS1 by its degrees of freedom? That is sigma 1 hat square, right. Same thing we are doing here. Here we are assuming that sigma square is a linear function of sum of all your explanatory variable, that is all. See, in that is, if that is the case, what we are trying to do, we are trying to adjust the error term of the original variable ui with an proper estimate of sigma square. And how do you get a proper estimate of sigma square? This is the way. Sigma square I, the traditional definition RSS by n minus k, which is the definition of sigma square from the Wallace model, is not working here in presence of heteroskedasticity. Instead of using that, what we are doing? We are taking RSS by n, that is all. Then we are adjusting our ui hat square by this newly estimated sigma tilde square and defining that as p. Okay. So, if at all this adjusted error term, if at all this adjusted error term has something to do with your explanatory variable, then obviously this p defined in this way should be explained by this parameter. So, that means basically from this model, what I am saying, from this model I am testing this hypothesis, lambda 1 equals to lambda 2 equals to lambda k equals to 0 or not, that I am testing, okay, that I am testing, alright. Similarly, in terms of the previous model, if you say sigma square, so from here what I am testing, this is my test, alpha 2 equals to alpha 3 equals to alpha 4 equals to alpha m equals to 0. So, obviously, then sigma square I would be, if this is rejected, then that means all these parameters are actually not equals to 0, that means sigma square I is something to do with the explanatory variable. But if it is not rejected, that means these are all 0, sigma square I equals to only alpha, you have constant error variance. That is the logic. So, we should understand the logic of this test, and logic is basically we are trying to modify some way or the other the RSS term, and then we are constructing the test statistic based on that. This is the RSS modified, then we are defining P we are regressing, then we are collecting the ESS, dividing it by 2, and that follows a chi-square distribution with m minus 1 degrees of freedom, where m is the total number of parameters to be estimated from the original model. Right? This is the procedure of Breusch-Pagan-Godfrey test or Bpg test. Now, what we will do? We will take the same data set what we are using yesterday, and then we will discuss about, we will see how to demonstrate this particular test in Stata. So, I have already imported the data. So, first what you have to do, you have to run your original model, where original model is reg consumption on income. This is your original regression. Okay, this is your original regression. And then from here what you have to do, you have to collect the RSS and you have to divide by RSS by n to get sigma tilde square, right. Now, what I will do, I will define the sigma tilde square. I am simply writing sigma square, sigma sq equals to, what is your RSS here? RSS, look, 2361 equals to 2361.15 divided by n, and what is your n here? 30, right. Then what you also do, you predict u comma residual, okay, and then you generate the square of u, gen u square, usq equals to u, this is u square. So, I have generated sigma tilde square, I have generated u hat square. Then how do you define your p? The p is just basically gen p equals to this u sq divided by usq divided by sigma sq. That is how I have defined my p. So, ui hat square divided by your sigma square, sigma tilde square. So, this is your p, and then you regress p on your explanatory variable. You have only one explanatory variable, which is income. And then what is your look at from this model. From this model you have to take your ESS, which is 10.42. So, if it is 10.42, then if you look at from here, if it is 10.42, that means your chi square calculated should be half into 10.42, 42 or 48, I will see. .42, right, 10.42. So, which is nothing but 5.21. So, this is your calculated chi square, Now, this calculated chi square you have to check from the tabulated, what is the tabulated value? Chi square tabulated at 5% level of significance equals to something around 3.23 or something. You can check the chi square value with m degrees of freedom. What is m here? M equals to 2. So, degrees of freedom would be 1. This chi square tabulated would be 1 degrees of freedom, because in your original model you have only 2 parameters, income coefficient and the constant term. This is 3.2. So, you can reject your null. That means this implies that chi square calculated is greater than chi square tabulated at 5% significance. So, at 5% level of significance, you can say that your data is suffering from heteroskedasticity problem.